Hello, myself Rohit Tillu. I am a student of Savitribai Phule Pune University and currently pursuing mechanical engineering. I am a serious rocket enthusiast and willing to participate in national competitions like this and looking forward for such competitions in future. This is my basic rocket design. This part is the nose cone part. You can see in this part, this is the nose cone. The main purpose of the nose cone is to reduce the drag. This is the forwardmost section of the rocket. The tangent ogive shape of the nose cone helps to reduce the drag by increasing the contact surface area. Also, this ogive shape, being a part of circle only, is easy to manufacture and to fit on the cylindrical tube. As we have kept the nose cone hollow, we can accommodate the payload inside the nose cone. Here you can see multiple parameters. This is the shoulder part. In general part, we can see the multiple parameters of the nose cone. It is attached at the frontmost part of the rocket. The second one is the payload, which is kept in between the nose cone. Here the payload allowance of the rocket is around 350 grams, but I have placed the payload of 300 grams for having the tolerance of some weight. Mostly for such type of rocket, the payload is like a microcontroller like Arduino board or Arduino Uno or combinations of microcontroller and multiple sensors. Here we can see other parameters of this. The next part is the next part comes to be as a body frame. The body tube is the main airframe of the model. The material here used is the balsa wood, as the strength to weight ratio of the material is very higher than many other materials. The purpose of the body tube is to hold everything in place and provide the required support to the components. There are multiple bulkhead and centering rings to support and keep everything in place. Here the material of the body frame is balsa wood, which has the best strength to weight ratio compared to many other materials. In this general section, you can see multiple parameters and the material which we have assigned. This part, the motor section part, shows how we have arranged the motor. Here we are using single motor, so there are no multiple parameters for motors. The later part comes as a recovery system. The recovery system consists of the parachute, the shock cord, and the parachute ejection system. The parachute's main purpose is to reduce the ground hit velocity to as minimum as possible during the descent of the rocket. It has the diameter of 45 mm, 45 centimeters, and which is made up of a nylon material. It is connected to six shroud lines which will maintain the shape of the parachute during the descent. At this point you can see the apogee. The deployment of the parachute will happen at apogee plus 2 seconds. That means after when the point at which the velocity of the rocket is 0 is called as apogee, the extreme topmost point. After that, plus 2 seconds after that point, the parachute will get detached. Along with the parachute, we have connected a shock cord. The one end of the shock cord is connected to mainframe, where the other is connected to the shoulder of the cone. The shock cord's purpose is to absorb the shock while the ejection of the parachute. Here you can see multiple parameters of the same. This is the mass and length, diameter, etc. Later, the parachute ejection system comes. This system has the piston which has given a tension with the spring, and one end is connected to the microcontroller. After the extreme point or the extreme altitude plus 2 seconds, this will give an activation call to the piston and it will get released and parachute will get ejected. The next part is the flight control board. It is the Tensi 4.0 microcontroller used and are connected with the multiple sensors like barometer, SD card reader, gyroscope, and connected with the LiPo battery. This system will help the rocket to decide when and where and what to decide and what to do the action. This is the fin. The purpose of the fin is to maintain the flight trajectory during the flight. The design of the fin must be such that the drag is maximum. Here we can take an example of an arrow. The arrow has the feathers at the tail, which has the most of the drag, because of which the arrow travels in the straight line. This is the general shape of the design, the general shape of the fin. We have considered the appearance as well as the center of pressure calculations for making this type of fins. This specific weight is given for the nozzle. This is an innovation part I have tried to do in this project. I have designed the nozzle shape and done its analysis on SolidWorks, and we can't show this on this software, so I have given the weight dimensions weight criteria in this for later simulation calculations. Here comes the motor part. The last but not the least, the main part of the rocket is the motor. I am using a Clarisonic Technology Incorporation company's G54RL5 motor for my rocket. The dimensions of this motor are: the diameter is 29 mm and the length of motor is 187 mm. This motor follows all the rules of the competitions, like the motor has an impulse of 160 Newton second only. Along with the burn time of 2.99 seconds, the propellant mass is 97 grams. As the launch mass is 198 grams minus empty mass of 101 grams is equal to mass of the propellant, which is 97 grams. Here we can see the chart of the motor thrust curve. This shows the impulse and thrust curve properties. This is the weight of the motor, the weight of the rocket without the motor, and this is with the motor. You can see the weight constraint is also being followed as the rule book was given. Here in this section you can see the length is 60.9 centimeter, maximum diameter is 4.5 centimeters. These are the CG and CP calculations, I mean the distance from the nose cone. This is the 3D figure. You can see it shows the internal part of the rocket. This is the 3D unfinished figure where you can see a multiple material structures and the parachute stuff. Where is the CG located? Where is the CP located? The blue color part is the center of gravity where all weight of the body is concentrated. This is the finished 3D rocket design. I have given some stickers on it which I like the most, and color as per my So this is the basic design which I have constructed. And now here comes the simulation part. Here the simulation is going to be run and see the calculation how it comes out to be. Here I have run the simulation. You can see the configuration of the motor in the first part, the velocity of rod, the apogee, which is 1009 meters. That is, it is also following the constraint of going above 1000 meters. The velocity at the deployment is 16.6 meter per second. Optimum delay of the motor is 11.3 seconds. Maximum velocity is 145 meter per second. Maximum acceleration comes to be as 129 meter per second square. The time required to reach the apogee is 14.3 seconds, and the total flight time including after the apogee and ejection of parachute is 114 seconds. The ground hit velocity is reduced to 9.93 meter per second. These are the basic results of the simulation which we get by this software. Later in the section we can also see the plots and multiple parameters are plotted against multiple parameters like time and altitude, time and thrust, and many more. We will see this in a further section. Here we can see the plot section. We can plot multiple parameters in this section like time with respect to altitude, vertical velocity, vertical acceleration, and many more. Here are some examples. What we can see like apogee, launch, etc. We will select all and plot the graph. Now we will see here. This is the graph of vertical motion with respect to time. Here it is given as altitude, vertical velocity, vertical acceleration. Given a multiple y axes, like for altitude it is different, vertical velocity and acceleration it's different. You can see the color they are given for specific stuff. Like this we can zoom the stuff. The red color portion shows the altitude, and the straight lines which you can see is the launch time, apogee, and multiple parameters are given. The blue color is the vertical velocity and the green is the vertical acceleration. Like this, you can pan to the normal view by clicking on this icon. This is the simulation of altitude with respect to time. Out the apogee, parachute ejection system, and ground hit. Here you can create custom options also. This is the custom menu. Here is the x-axis point. This generally we take as a time. Here is the y-axis, which you whatever you can choose to plot with respect to time. Here I am choosing the propellant mass. Okay, first we will choose thrust and later we will choose propellant mass. Now we will plot the graph for the same, considering all the parameters. Here we can see this plot. Now we will zoom the plot and see what are the parameters. Here you can see the thrust is in red color and the propellant mass is in blue color. The bottom portion shows the time and the thrust curve. Here you can see the propellant mass is decreasing, and before the burnout, before 3 seconds, we have a burnout time of 2.99 seconds. So before that it goes to 0 and later it remains constant. Like this, in this section you have multiple parameters you can plot with respect to time or with respect to multiple parameters. In this section you can export your data as a CSV file. Thank you for showing interest in my design. This is all I wanted to tell you. This is also a Photoshop, we can say, the software which is providing. And thank you for SDNX and Helium Learning Labs for giving me this opportunity and making me learn new things and creating an opportunity and platform for learning such kind of things. Thank you.